Today we're going to study the properties and some applications of matrices. I think most of this will seem pretty easy for you. The hardest part is going to be writing down your work. And remember, that is where you get your points, is by showing your algebra. So let's give it a whirl here. First of all, matrices are considered equal when two matrices have the same dimensions and every corresponding element would be equivalent. If matrices are of equal dimension, then you can start applying any operations to them. The first two will apply are addition and subtraction. So in problem A, what is the dimension of the first matrix? We say 3 by 1, 3 rows, 1 column. The second matrix is also 3 by 1, so we should be able to add those. And this is where you're going to show your work. Element 1 plus element 1, 0 plus 1, 4 plus negative 9, 3 plus 8. And it results in the matrix 1, negative 5, 11. Both of these pieces are going to be needed to show to give you credit. Now let's try matrix B. Dimensions of the first one, 2 by 2. And the second one is also a 2 by 2. So my result should be a 2 by 2. 3 minus 2. 3 minus 0. 9 minus negative 3. Negative 5 minus 5. Gives me a result of 1, 3, 12, negative 10. In matrix C, my first matrix is 1 row, 2 columns, so a 1 by 2. My second matrix is a 2 by 2. So you should not be able to add them. And I'm going to prove that to you. If I tried to add, I would have 9 plus 1, negative 7 plus 3, and then I don't have an element. There's not a single thing there for me to add to 4, so this is where it becomes not possible. Let's say matrix A is 1, negative 2, 3, 2, negative 4, negative 1, 4, 0, 5. And matrix B is 0, 1, 1. X, 3, negative 2, 2, 4, negative 3. They're asking, what is A12, B31? A12, matrix A, row 1, column 2 is a negative 2. So we're going to replace this with a negative 2 times B31. Matrix B, row 3, column 1, brings me to 2. Negative 2 times 2, negative 4. And that's the work I would need to see. this time it says if A21 equals B21, what is the value of x? Matrix A, row 2, column 1. Row 2, column 1 equals matrix B, row 2, column 1. X would equal 2. Now we have a thing called scalar multiplication. It's when you multiply each entry by a scale out front. In geometry, you use scales. You would make a scale of 1/2. So you'd make every length half as long as the previous length. Same idea here with scalar multiplication. My scalar in letter A is 6. So I'm going to take that scalar times each element of this 2 by 2 matrix. So my work matrix would be 6 times 2, 6 times -3, 6 times 8, and 6 times 4. And my result, 12, -18, 42, 24. I need both pieces to give you full credit. So in this second matrix, I have a scalar of -1 first, and then I'm going to add it to this matrix. So I could show all my work in one matrix. It will be a -1 times 4, then I'm going to add 3. A -1 times -7, add 6. -1 times 3, add 9. -1 times 3, add -8. -1 times 2, add 1. -1 times -9, add -4. Results in -4 plus 3, -1. 7 plus 6, 13. -3 plus 9, 6. -3 plus -8, -11. -2 plus 1, -1. 9 plus -4, 5. If you would choose to show the scalar multiplying matrix first, then the adding matrix, you can do that. As long as you show work and then a result. So this one says solve for x and y. So I have a scalar on both matrices of 4. I'm adding them, and I have equivalent matrices. So according to order of operations, we would do the adding first. I'm just going to write this 4 out front. And my work would be 8 plus 4, 0 plus -2x, -1 plus 1, and 2y plus 6. Should equal 48, -48, 0, and 8. So then, when I scalar through, I have 4 times 12, 4 times a -2x, 4 times a 0, and 4 times 2y plus 6. So again, equal 48, -48, 0, 8. So if I check this out, 48 equals 48. -8x equals -48. -8, that means x is a positive 6. And then 0 equals 0. $8y plus 24 equals 8. 16 divided by 8, y equals a negative 2. Let's apply matrices to a life problem. We have a condominium owner that paid yearly fees to cover the cost of maintenance, landscaping, and remodeling. The fees this year are $96, $18, and $66 for a 1-bedroom, $128, $24, and $88 for a 2-bedroom. Next year's fees are $105, $20, $73 for the 1-bedroom, $141, $26, and $97 for the 2-bedroom. Use a matrix to organize your information. Use those matrices to find the monthly changes in fees from this year to next year. So if I'm going to find a change, I'm going to have to take next year minus this year. So I have 3 costs and 2 units. So I'm going to say maintenance, landscaping, and remodeling. And I'm going to put that 1-bedroom and 2-bedroom. So first I need next year. So next year, 105, 20, and 73. For the 2-bedroom, 141, 26, and 97. And I'm going to subtract the same one, only for this year. So the 1-bedroom was 96, 18, and 66. 2-bedroom, 128, 24, and 88. So then I will get 105 minus 96, 141 minus 128, 20 minus 18, 26 minus 24, 73 minus 66, and 97 minus 88. Which results in 9. 21 minus 128 is 13. 2, 2, 7, and 9. Now that's on a yearly fee, and we wanted monthly changes. So then I would take 1/12 times it all. So it would be 9/12, 13/12, 2/12, 2/12, 7/12, and 9/12. Now we're going to multiply matrices. And this is the one where you're going to have to pay close attention, and you may actually have to pick up your fingers and touch to get it to work. So first of all, matrix A times matrix B should equal AB matrix. Notice the dimensions on A, M by N, and B, N by P. The dimensions of the columns of A must be the same as the rows of B. And your resulting matrix will then have rows of A by columns of B. Then your matrices will actually multiply. If we make a mapping of the elements, we know which rows and which columns to multiply by each other. So And let me give you an example. Let's say simply matrix A is a 2 by 1 X, Y. Matrix B is a 1 by 3 R, S, T. So first check. Do your columns match your rows? Yes. So my resulting matrix should then be rows by columns, a 2 by 3. So then I create 2 rows with 1, 2, 3 columns. This blank is in row 1, column 1. This blank, row 1, column 2. This blank, row 1, column 3. This one, row 2, column 1. Row 2, column 2. Row 2, column 3. So then I must take row 1 by column 1 when I'm filling in my first blank. Row 1 by column 1. XR. Next, row 1 by column 2. Row 1 by column 2. XS. Next, row 1 by column 3. XT. Row 2, column 1. Row 2. By column 1. YR. Row 2 by column 2. YS. Row 2 by column 3. YT. Well, that's the easy one. But as we know, each row and each column can have more than one element. So if you have more elements, you're going to find it when you multiply a row by a column to sum all those products. So let's try a little bit more complicated one. First, matrix A, 4, -2, 3, 0, 1, -1. Matrix B, 1, 5, -3, 2, 0, 4. It says to take matrix A times matrix B. So what are the dimensions of A? 2 by 3. 2 rows, 3 columns. What are the dimensions of B? 3 by 2. 3 rows, 2 columns. Do your inside dimensions match? Yes. So then your result is going to be your outside dimensions, a 2 by 2 matrix. So I'm going to start with the map. 2 rows, 2 columns. This one is in row 1, column 1. Row 1, column 2. Row 2, column 1. Row 2, column 2. So then I'm going to take row 1 and multiply it by column 1. And I can use my highlighter. This is row 1 by column 1. Now take your fingers and touch each product. 4 times 1 is 4. Plus -2 times -3 is 6. Plus 3 times 0 is 0. When we move to row 1, column 2. I have to pick up my fingers and move it. So I have 4 times 5 is 20. Then I have negative 2 times 2 is 4. 3 times negative 4 is a negative 12. Next position, row 2, column 1. Row 2, column 1. So now row 2, column 1. 0 times 1, 0. Plus 1 times negative 3, negative 3. Plus negative 1 times 0, 0. Then my next position, row 2, column 2. 0 times 5, 0. Plus 1 times 2, 2. Plus negative 1 times negative 4, 4. Results in 10. 24 minus 12 is 12. Negative 3, 6. Now let's try it the other way. Let's see. Let's try matrix B times matrix A. I actually have to rewrite them so that they're in the right order. So matrix B, 1, 5, negative 3, 2, 0, negative 4. That is a 3 by 2 times matrix A, 4, negative 2, 3, 0, 1, negative 1, which is a 2 by 3. Will it multiply this way? Your inside dimensions work. So on the outside, you should get a 3 by 3. So I create 1, 2, 3 rows and 3 columns. This one is in row 1, column 1. I have row 1 by column 1. 4 plus 0. Row 2, excuse me, row 1, column 2. Row 1, column 2. 1 times negative 2 is negative 2. Plus 5 times 1 is 5. Then, row 1, column 3. 1 times 3 is 3. 5 times negative 1 is negative 5. Next is row 2, column 1. Negative 12 plus 0. Row 2, column 2. 6 plus 2. Negative 3 minus 2. And then I have my last row by each column. 0 times 4 plus negative 4 times 0. 0 minus 4. 0 plus 4. Results in 4. 12, 8, negative 5, 0, negative 4, 4. Is matrix multiplication commutative? When I switched the order that I multiplied in, did I get the same answer? No. That is the property that will never work in multiplication of matrices. Let's try one more. Matrix C, 8, negative 5, negative 1, 2. Matrix D,
Dial extension
4,
1806.
negative
Adam
3,
Payco, please
0,
dial
1,
1806.
2, negative 6. Matrix C is a 2 by 2. Matrix D is a 3 by 2. Do these dimensions match? No, they don't. So it should not work. Even if we tried, here's where we would have row 1 by column 1. And look at, we would end up with 8 times 4 plus negative 5 times 0 plus, I don't have an element to multiply by 2. So do you see why those inside dimensions must match for it to multiply? It just won't work if they don't match. Recall that we said matrix multiplication is not commutative, but it is associative and distributive and associative with a scalar. The only property that does not work in multiplication is commutative property. You should now have enough information to do your homework.